So good morning, everybody. My name is Wilmer, and I'm here to give my talk on 2D magnets and magnetic dope materials. So just kind of briefly outline what my literature review is going to be about. I'm going to give like a brief introduction on what I found and why this is relatively relevant. Talk a little about 2D magnets and some specific materials in general. Talk about dilute magnetic semiconductors and how they also play a key role. And then kind of talk about some of the challenge that's faced versus theoretical versus experimental calculations, and then give a brief overview of closing remarks on this. So since the discovery of 2D materials, it's been something of interest to try and find 2D magnetic materials that we could use in application. So for like 2D magnetic devices as well, we want to try and find certain properties that we can get ferromagnetic or anti-ferromagnetic coupling, because we want those switching devices, for example, in memory applications for ones and zeros. And this provides great potential for next generation of devices, either to reduce the overall area or have higher efficiency as well. And also this gives more about some of the quantum effects that we get within the materials that we can get for experimental research as well. We could see how these layers interact individually within layers themselves or between the layers as well. However, there had been problems that people were running into, that it was very difficult to try and get magnetism in the 2D limit, since as you reduce the thickness of your material, you actually lose the preferred desirable order of magnetism that you want. And the reason for this is that you reach a critical temperature, as we hear it talked before, for certain materials, and you actually lose that order of magnetism as well. So some of the key things that people were looking for to try and battle this was trying to find materials that have either higher Curie temperatures, or as we've learned in this class, you could actually look at the magnetic anisotropy energy, or that energy barrier, to try and increase the amount of energy needed to get that switching. So some of the first successful 2D magnetic materials that were found actually have it in the graph up to the right. One was chromium iodide, and the other was chromium, germanium, telluride are some examples. And this was huge because now we had actually seen 2D magnetism, but this doesn't give the whole story, as it turns out, as you go to the monolayer limit, some of these materials actually don't keep their magnetism. For example, chromium, germanium, telluride, there is a reason why there's no graphing point as you get to one layer. And this is because of the fact that magnetism from your bulk material actually doesn't necessarily mean you'll have that same magnetism in your layer as well. And the reason for this is that your critical or Curie temperature is proportional to your spin dimensionality, or how many dimensions you're working with. So it would be something of interest to try and find some critical thickness of where we see this line between where we lose this order of magnetism, and could we get materials that possibly have higher Curie temperatures. So I'm going to go ahead and highlight chromium iodide, which is one of the successful findings for 2D magnetism. It's a semiconductor, and experiments that were done on this to try and find why it was able to keep its magnetism through one of these effects was through magneto-optical Kerr effect, which it gives us the direct relation between how light interacts and reflects off magnetized surfaces. And this angle of reflection is actually related to the magnetization. So if I could direct your attention to the graph to the right, this is actually some graphs between 1 layer, 2 layer, and 3 layers of this material. And some interesting finds that we find is that when we have an odd number of layers, we actually are able to see hysteresis around 0 applied field, which shows us that there actually is this desired ferromagnetic state that we would like in materials. However, when we have an even number of layers, we actually see that we have ferromagnetic ordering with higher applied fields, but at lower fields, we actually are in this anti-ferromagnetic state. So this actually tells us a lot about between the coupling exchange, either within individual layers, which is interlayer, or between the layers, which is also interlayer. And there also have been some measurements done with applied voltages as well. They've used this in MTJs. And we can also see how we get this same kind of correlation between even number of layers with applied field. We see this kind of spin flipping at certain applied fields as well. And this could sort of help us to see maybe what critical thickness we could get to see this different switching and ordering. So another material that shows 2D magnetism is iron germanium telluride. This is a metal. And I didn't mention this earlier, but the chromium iodide is actually, you're able to get it through exfoliation through your bulk material. Whereas typically for this material, you do it through some kind of vapor deposition technique or molecular beam epitaxy. And similar tests can be done on this. The difference between the chromium iodide and this iron germanium telluride is that I mentioned that for chromium iodide, you have ferromagnetic ordering within the layers, while you have antiferromagnetic between them. But here you just have strictly ferromagnetic between and within the layers as well. And because of this, we can actually use these as electrodes and MTJs as well. And we can apply a gate voltage bias, and we can get many measurements to try and compare how they might compare between the individual layer and their bulk material as well. So we can kind of see how we could get the resistance or TMR value as well at certain spin flips as well. And then one of the interesting things is in the top right graph, we can see how when we apply gate voltage, we can manipulate both the coercive field and also the Curie temperature to get some desired value, which is actually really cool because you can see that we can actually get the Curie temperature of this material to almost room temperature, which is ideal for us because if we're going to use these for device applications, we need at least to have that in our materials as well. So another topic of interest is doping these magnetic materials as well. These materials are very hard to fabricate and could also be very rare. So one way we could counter this is to try doping our materials. Specifically, hole doping is one of the ones that I found in literature most often. So this actually helps with long range order, which is what we would want. We want to try and keep the Curie temperature high so we can have that favored magnetic ordering. And in literature, I found that some of the most promising or wanting experiments were trying to get these with the gate bias and MTJs, as I had read that there had been a lot of sort of experimental calculations to try and get more efficiency out of them in MTJs rather than your typical spin transfer torque or spin orbit torque MTJs. However, they did not sort of allude more on that, which I guess they're still in the works right now. So you can dope these with holes, but you could also get this ferromagnetic state ordering either through intrinsic defects or through acceptor impurities. And some of the ways that you can consider what maybe a good DMS material is either through spin polarization energy, which is essentially just the correlation between the energy you have in a non-ferromagnetic state of your material versus the ferromagnetic state of your material. And another identifier of this is how many Bohr magnetons you have per hole carrier. So the reason why we would want that is you typically want to have a 1-to-1 ratio between Bohr magnetons and a hole carrier. The reason for this is we don't want any vacancies within our actual structure, but you also don't want too many to where you're getting kind of this clustering as well too. And this is just an example of some materials you could have with halogens, but there's also other types of materials that are used like halides, or as we've seen in class, you can have oxides also mediate this kind of exchange as well. So some of the challenges that are still faced with these materials, with chromium iodide, the Curie temperature I had seen had a range between around like 40 to maybe 70 Kelvin. And this is great, but it's still relatively low compared to room temperature. So ideally with most of these other materials, we're still trying to find ways to try and increase this. There are materials that do exhibit higher Curie temperatures within thousands of Kelvins range. However, these are very rare materials or are very difficult to try and produce. I mentioned some ways to try and synthesize these materials. The most popular ones being exfoliation and MBE. Exfoliation is probably the most popular with most of these as you get less defects and smoother surfaces. However, it still has its drawbacks. It's not time efficient. So there's that. We also have the issue of controllability as well. We want to be able to have good materials. We want materials that can be more air controlled, that work at room temperature, even above that. And you can control this with DMS materials as well, but I mentioned how you could have dopant clustering that can actually reduce your Curie temperature, or it could also lower the saturation magnetization as well. Even with these challenges, there's promising upside to this topic in general. It's still relatively in the early stages, even up till now, to be able to use in future device applications as well. This also gives us experimental means of understanding quantum interactions within materials too, and also giving us the relationships and couplings between layers within the bulk. We could see how 2D layers relate to their bulk material, or how we could get 2D materials that exhibit maybe some desired magnetism, and maybe get it to some bulk material as well. So with that, that's my presentation.